Hi friends. So today I'm starting this new lecture series, and today we are going to look at the first part of this lecture. So we are going to cover some of the basics as far as aerodynamics is concerned. I'm Dr. Ranjan Ganguly. Now the first thing we are going to look at are some fundamental flow quantities or physical quantities of air. And these are essentially valid for any fluid, but we are going to concentrate more on air. Then we are going to define the concept of a flow field, which is very important as far as the aerodynamics is concerned. So let's look at the first of these four quantities, and that's pressure. Now, as you can see here, pressure is defined as the limit of dF by dA. So essentially, in terms of calculus, that's an instantaneous property here. So if we go back to physics and think about pressure, it was essentially defined as the force per unit area. And this is exerted on a surface here because there is a time rate of change of momentum of the air molecules impacting on the surface. So you can picturize this body being in air, and all these molecules are coming and they hit this surface, and so pressure is generated. Now essentially, as dA tends to 0 in the limit, you are going to get the instantaneous pressure at any given point. So that brings us to an important question or important point, is that pressure P is a point property, and therefore it's going to have different values at different points. So if we are in a room, for example, the pressure is going to be different at different points in the room. And certainly if we are out there in the atmosphere, there is a difference in pressure at any given point because this is a point property. Now going back to the units, the unit of pressure is Newton per meter square. Now let's look at the second point property, and that's density. Now the density of air is the mass per unit volume. So again, this is coming to us from basic physics. And today we are going to look at the instantaneous property. So essentially that is rho, that's the limit of dm by dv as dv tends to 0. So in terms of calculus, this is going to become a point. Now here when I'm talking of dm and dv, I'm thinking of a small cube like this, and as this cube becomes smaller and smaller, this becomes a point. Now again, theoretically, density being a point property is also going to have different values at different points. So if we are looking at the atmosphere, the density is different at different points in the atmosphere. Now let's look at some measure for density. So let's imagine that there is a room. Maybe you are sitting in this room right now, and this has a volume of 250 meter cube. If we were to take the mass of air in that room, that would be, let's say, 306.25 kg. And if this is evenly distributed throughout the room, then the density would come out to be 1.225 kg per meter cube. So again, this is a number to remember. This is the density of air, and we use it all the time in the aerodynamics field. So in general, if we have a uniform density situation, we can take this kind of value. Now again, you know from basic physics that the unit of density is going to be kg per meter cube, because it's mass divided by volume, the unit of mass being kg, the unit of volume being meter cube. Now that brings us to the third property, and this is temperature. Now we can think of air as a collection of molecules and atoms, and all these particles are in a constant state of motion, and therefore there is a kinetic energy which is associated with air. Now the temperature T of air is going to be directly proportional to the average Ke of the system. So let's look at the physics behind it. If we say that Ke is the mean molecular kinetic energy, then the temperature is given by Ke is 3 by 2 K into T. So you can see clearly that Ke here is directly proportional to temperature, and there is this constant here which essentially defines this relationship, and this constant is known as the Boltzmann constant. So it's given by 1.38 into 10 to the power of minus 23 joule per Kelvin, very small number. Now, essentially, whenever we are dealing with equations in this subject, we are going to always use Kelvin. So again, just to remind you, if the units are Kelvin, centigrade is Kelvin minus 273.15. So for example, if we are at 0 degree centigrade, then that corresponds to 273.15 Kelvin. And if we are 0 degree Kelvin, that's minus 273.15 C. So again, temperature is a point property and 0 Kelvin is very, very cold. So we come to the fourth quantity, and this is a vector quantity. So essentially here we have flow velocity, and because it's velocity, it is essentially speed and direction. So speed and direction are going to vary from point to point in the flow, and this is going to make it a point property. So again, we can imagine an airfoil section. So this section I have drawn here, this is a typical airfoil section which is used in the wings. So if you check out any aircraft wing or helicopter rotor blade, you are going to find the section is something like this. And the reason this section is used is because it has very good properties in terms of being being able to generate a high degree of lift with relatively low drag. So let's look at the flow on top of this airfoil. So essentially the flow is going to go like this, and let's say we take any fixed point B. Then if we take a small cube here of fluid, then this velocity of air as it sweeps through this point is going to be that specific property here at this point. So that's a point property. Now here we are assuming that the flow is steady, which does not fluctuate with time. So that's another technical definition. Steadiness means that you are not fluctuating with time. So corollary of that would be unsteady flow, where you are fluctuating with time, where your velocity is fluctuating with time. So if you are in steady flow, this moving fluid is going to trace a fixed path in space, and this path which I have indicated by these lines here are known as streamlines. So this is a very important concept in flow, and streamlines are not just an abstract concept, they do exist in practice. If you put an airfoil section in a wind tunnel and put smoke filaments through it or pass smoke filaments through it, then you are going to see that the streamlines actually are there, and you can actually visualize these streamlines. So you can think of the flow velocity taking place in terms of these streamlines. So now we are going to summarize this very important theory which we have learned now, and that is that there are four basic aerodynamic flow quantities, being the pressure, the density, the temperature, and velocity. So that's P, rho, T, and V. And I have made V bold here because V is a vector. Now, knowledge of these four quantities at every point of a flow essentially fully defines the flow field. So let's assume there is a system here and we fix a Cartesian coordinate system here. So this is X, Y, and Z. So essentially what happens is that at any point in this three-dimensional system, there is going to be a pressure, that's P is P, X, Y, Z. There's going to be a density similarly defined, temperature similarly defined, velocity similarly defined. So what it means is that at any point in this system here, or this three-dimensional system, there is going to be a pressure, a density, a temperature, a velocity, and these are all going to be point properties in this flow field. So now we look at the more important thing from practical perspective, and that is the aerodynamic forces. Now essentially a practical consequence of air moving on top of an object is that the object is going to experience a force. Now you are familiar with this in real life. For example, if you are sitting in a car and you just put your hand out of the window, it's going to feel a certain force. So again, that force is due to the drag which is being created by the presence of your hand in the air. Now, similarly, a more practical use of this phenomena could be that if you go to the sea, you are going to see some of the boats which are sailing with sails. So again, this was the primary means of transportation in the centuries bygone. And so essentially, these sails generated forces which could be used to move the boat through the water. Now, similarly, a more practical and in some ways closer experience is that if you were to throw a ball, for example, if you are playing cricket or if you are playing baseball or any of these type of sports, then essentially this ball also experiences a force due to the wind, and sometimes that is going to cause a swing in the ball and so on. So these are some facts which you see in reality. The fact that whenever you are trying to move through air, you are expending force or you are experiencing a force. So essentially we can classify all these type of forces into two subtypes. So essentially let's look at any source of aerodynamic force, such as you get forces on surface of cars, wind turbines, airplanes, balls, missiles, helicopter, drones, ships, etc. And all these are going to come from two simple natural causes, and these are number one being pressure distribution on the surface, and number two being shear stress or friction on the surface. So if we look at each of these forces in detail, the pressure distribution in surface, this acts normal to the surface and varies with location. And so there is going to be a net unbalance of pressure distribution which is created by the aerodynamic force. Now if we look at the shear stress phenomena, which is because of friction on the surface, this always acts tangentially on the surface and it varies with location. And this is due to the flow having a rubbing type of phenomena on the surface as it moves around the body. So now I'll show this pictorially. So if you again look at an airfoil, you can see here that the pressure essentially acts normal to the surface. So all these arrows here show the pressure is acting at different points, and these are all normal to the surface. So that's the pressure force. And here we see that this tau W, this is tangential to the surface. So this again acts at all the points on the surface, but this is tangential to the surface. So prediction and measurement of this P and tau W on the surface are very important, and essentially if we want to calculate these, or we even want to calculate these using measurements, we need to know the complete flow field. So that's the importance of the flow field. That's why we need to know pressure, density, temperature, and velocity. So let's now look at some of the equations which are going to relate the different quantities in the flow field. These are not quantities which can take any arbitrary value at all given points. So there are certain physics or physical phenomena which relate these quantities, and the first one of these is the equation of state. So now if we look at the equation of state, it's essentially going to just work on one point here, and the remaining equations are going to work on 2 points. So we are going to look at all these equations just to recapitulate. Remember, P, rho, TV are the four basic aerodynamic flow quantities. Knowledge of these four quantities at every point of a flow will fully define the flow field, and the flow field is given by a knowledge of all these points at every point x, y, and z. So what happens in air is that air behaves as a perfect gas in normal conditions of temperature and pressure. And a perfect gas is one in which the intermolecular forces are negligible. So fortunately for us, air is a perfect gas, and in air, essentially this equation holds, that is P is rho RT. Now, like I mentioned, this equation holds at any given point. So if you are at any point and you know any two of the quantities, let's say you know rho and T, you can calculate P. Or if you know P and rho, you can calculate T and so on. So here the constant R is very important, and this R is 287 joule per kg Kelvin. So that's essentially something which is known as the gas constant for air. So if you want to solve any simple problem, we can always use this equation here. For example, just to illustrate, the air pressure and density at a point on a wind turbine plate are given by these two numbers here. So what is the temperature of this point or at this point? So again, we go to this equation here. We know that T is going to be P by rho R, and so we can calculate it. Now, whenever you use this equation of state, the main thing to remember is that temperature is going to be in Kelvin. Pressure should be in Newton per meter square, and density should be in kg per meter cube, and of course R is 287. So if you use these units and these numbers properly, you are going to get the right value. Don't use centigrade here. Now the next equation we are going to look at is the continuity equation. Now, before going to the continuity equation, just make a point that all these equations we are going to consider now, they are essentially coming from certain basic physical principles which you are all familiar with. So number one principle being mass is conserved, that's going to be used to get the continuity equation. The number two principle is momentum is conserved. With that we are going to get the Newton's second law or Euler's equation, and the integrated form of Euler's equation, which is Bernoulli's equation. And if we were to also consider energy is conserved, we get the energy equation from that physical phenomena or physical principle. So let's look at continuity equation. Now let's look at something like this. So this is a stream tube, and we are going to consider mass conservation here. Now we know that mass can neither be created nor destroyed. So therefore continuity equation is there for steady fluid flow. What we are going to derive here today, very simple form of this equation. And the assumption here is that velocity and density vary uniformly over cross section A. So the velocity and density here are the mean flow values, and this assumption is reasonable for many applications. So for example, here I have rho 1, V1, A1, here I have rho 2, V2 and A2. And so I can say that M1 dot, which is the mass flow rate, is equal to M2 dot. And so these are equal to rho AV and rho AV. So V being the velocity. So essentially, whatever is the mass flow rate here is the mass flow rate here, and this equation is known as the continuity equation. Now, in many cases, the density is going to be constant. So this is the case where you have incompressible flow. And so rho 1 and rho 2 are going to be equal. So you get a very simple form of the continuity equation, which is often used in various types of flows, such as through pipes and so on, through stream tubes and such bodies. Now, incompressible flow is an excellent assumption for the flow of liquids such as water or oil. But for air, it is only valid at low speed. So if your air velocity or the velocity of the body through air is less than 100 meter per second, then incompressible flow is a close approximation, or else you have to consider compressible flow, which is much more complicated. So now let us look at the next equation, which is the Euler equation. Now you clearly saw that continuity equation linked the rho and V across 2 points. So it never talked about pressure. So again, if you are going to look at pressure, that's important because pressure is the thing which is going to give us the aerodynamic forces acting in the body, because if we know the difference in pressure in the fluid from point to point, essentially we can calculate the force which is acting. So let's look at a body or a small mass which is there in a streamline, and this mass has a pressure P and a velocity V which goes with it. Remember, those are all point properties. So now what we do, we take this element of fluid out. We say that its dimensions are dx, dy and dz, and pressure acting on one surface is P, and on the second surface is P plus dP by dx into dx. Okay, so pressure acts in the normal direction on all six faces, but we are going to only consider one direction because we want to form a very simple form of this equation. So frictional shear is of course going to be there, but right now we are simply going to neglect this frictional pressure. So gravity is also going to be there acting on this mass, but again it's going to be small, and so we are going to neglect it. So it's small relative to the pressure related forces. So with that assumption behind us, or we have made, and we are going to now look at this element of mass here and try to apply Newton's law to it. So let's take this mass here, dx, dy and dz, pressure P plus dP by dx into dx. So net force in the x direction is going to be P into dy dz. Remember, that is the cross section on which the pressure is acting, and the force on the second side into dy dz, and that gives us this equation here, minus dp by dx dx dy dz. Now we know that this small piece of fluid which is there, being a cube, it's going to have a volume of dx dy dz. So I can say mass is going to be rho into dx dy dz. So if we think of acceleration, that is dv by dt or dv by dx dx by dt or dv by dx into v. So now I take Newton law, F is ma, I plug in all these values, I plug in the force, I plug in the mass here, I plug in a, I do some cancellations of dx dy dz, and I get dp is minus rho v dv, and this is the Euler's equation. Now this equation is valid for inviscid steady flow. So that's something to keep in mind. Inviscid simply means there is no viscosity, okay, and there is no viscosity, so there is no friction. That is an assumption we have made here. We are assuming only pressure forces are acting on this body. There is um, no shearing or no friction type of force here. Now the next equation we are going to look at it in today's lecture is the Bernoulli's equation. And we are going to look at the Bernoulli's equation because it is something which can be derived from Euler equation, and it gives us relationship between 2 points in the flow field. So if we look at the Euler's equation, it's a differential equation. So it describes the phenomena in an infinitesimal neighborhood of a point. Again, we saw it's valid for both incompressible and compressible flow because we didn't make any approximation or assumption about density. Now to get Bernoulli's equation, we consider an airfoil, we consider a streamline, and we take 2 points on the streamline 1 and 2, and we are going to integrate Euler's equation at these 2 points. So if I integrate it P1 to P2 and then V1 to V2, I can do this integration provided I pull rho out of the integral. And to pull rho out of the integral, I am essentially making an approximation of incompressible flow here. I get this integrated form, and so then I get this equation here. So pressure plus rho v square by 2 is equal to constant along a streamline. That's essentially the Bernoulli's equation as far as the aerodynamics is concerned. Now knowing this equation, if I have any of these variables, say if I knew P1, V1 and V2, I could calculate P2. And so if I know any three of these variables, I can calculate the fourth variable. So we can see that this Bernoulli's equation holds for inviscid incompressible flow. So remember, in deriving the Euler's equation, we did not account for friction, so it became inviscid. And then in deriving Bernoulli's equation, we took rho to be constant, so it became incompressible. Now for compressible flow, Euler's equation must be used. Bernoulli's equation should not be used for compressible flow. Now that's something to keep in mind, and both these equations are essentially a form of Newton's law, F is equal to ma. We saw that was the formula we used to derive the Euler's equation, and so essentially this is nothing but Newton's law for fluid flow. So that is going to end today's lecture, and today's lecture was essentially uh, an outline on the basic point properties and the three simple equations derived in their simplest form. So again, continuity equation, the momentum equation, and the Bernoulli's equation. So these were all derived today. And so now you know how to calculate some of these properties if you are given some different properties here. Now remember that in most aerodynamic texts you are going to find much more complicated equations. That's because they consider not only one direction, but they consider various directions. They also do not only consider steady flow, but they also consider unsteady flow. So there are going to be terms involving dv by dt and so on. So that's all very complicated and fine, but the aim of this course here is to just provide you a basic outline as far as the aerodynamic subject is concerned, so you can figure out what's going on and also understand many of the aspects which are required in say simple things such as how drones fly and how some of the simple things such as lift and drag can be calculated. And those are some things which we are going to discuss in the next two lectures. So I will stop this lecture now and I will see you next in my next video. See you then.